Hello, friends. Myself is Yashwan. Today, let us talk about the topic verification of OS for IoT in smart cities. Introduction. Formal verification mathematically proves if software meets design specifications in IoT systems within smart cities. Operating system verification is critical for ensuring secure and reliable functioning. Objective: this paper process using formal verification tools at the assembly level for IoT operating systems, focusing on verifying a micro operating system prototype. Background: traditional software development methods use testing to uncover vulnerabilities, but even when tests are passed, correctness is not fully guaranteed. IoT OS in smart cities are complex and correctness at every layer of software is crucial. For formal verification can be applied after development to prove mathematically that the system adheres to its design, especially in mission critical environments like smart cities. Formal methods in IoT. Formal methods were developed in the 1950s to provide mathematical proofs for system correctness. In the 1970s, formal verification gained traction for operating systems, expanding to critical infrastructure systems such as communication based train control. IoT, with its wide range of connected devices, requires rigorous verification due to security and reliability concerns. AL Notable research groups. Flith Group focuses on building large-scale verified system software using formal methods. Contribution include certified binaries and verified OS kernels. Trustworthy system groups. Tools like CAKEML, a verified compiler, and CAMKES show advancements in building trusted systems. Known for developing SEL4, the world's most advanced microkernel, and verifying it through the L4 Verified project. System model overview. A key focus of this research is modeling the x86 system architecture at the assembly level. Components: registers, memory, and common assembly instructions. Micro OS example. The MOS is used as a case study to demonstrate the method's feasibility for verifying in an IoT operating system for smart cities. The x6086 architecture involves 32-bit registers that store values for the CPU during execution. These registers are modeled in Isbell HOL using aliases for different bit sizes: 32-bit, 16-bit, and 8-bit registers. Example: EAX for the 32-bit EAX register, EDX for EDX, and so on. Memory model. Memory is represented as a mapping of addresses to 8-byte data and a mapping for instructions. Instruction memory, separately modeled for execution and simulating assembly instructions. Memory model examples use natural numbers for addresses to map byte values and instruction tuples. Operand model. Operands are crucial in assembly for specifying the data on which instructions operate. x86 architecture supports three types of operands: immediate data, registers, and memory references. Example: a 32-bit operand might be immediate data, or a register, or a memory references. Introduction to core segments. Assembly instructions vary based on operand bit size. Example instruction include NOP, no operation, add, addition, which has 8, 16, and 32-bit versions. Code segments are modeled as lists of instructions tuples that are executed step by step during verification. Simulation of execution. Functions in Isabelle HOL are used to simulate assembly instructions execution by reading or writing registers and memory. Examples include the functions to get the value of a register and function for reading or writing memory addresses. Single and multiple step execution. Single step execution simulates a single instruction by reading current memory, executing the instructions and updating the state. Multi-step execution executes multiple instructions recursively, modeling the continuous operations of a system. MOS feature. MOS Micro Operating System designed for IoT in smart cities. Features: boots with GRUB, handles interrupts basic memory and process management, interacts with user via a console and can run user programs. Allocation in MOS. MOS uses a free linked list to manage memory and a first fit algorithm for allocation. Example: when allocating memory for pages, it looks for a free memory area of the same size, modifies the free list, and allocates the memory. Assembly code handles deleting and modifying nodes in the free list. Verification of accessible assembly code. The paper verifies MOS assembly code for memory allocation. The assembly code is divided into functions, each responsible for specific memory management tasks. Code snips. Memory management functions are verified by providing their correctness in Isabelle and HL. Conclusion: the method successfully verifies IoT operating systems from the assembly level. It shows how formal methods can prove the correctness of systems even when dealing with complex architectures like x86. Limitations: large scale systems may require substantial computational resources for full verifications. Future work: extend the verification process to cover the entire operating system, use different logics for verifying different modules, potential applications for real world IoT systems where security and correctness are paramount. Thank you.